principle of least action. So like I said, so far this is pure optimization, right? This board is indeed has nothing to do with mechanics, right? Just to tantalize you a little bit more about the principle of least action, we will go to the entire lecture is about the principle of least action. It's history. But to tantalize you a little bit more, you know Feynman. I told you about this story before in the very first lecture, introduction lecture, but I'm repeating it again. You know Feynman, the great physicist, Nobel laureate, when he got Nobel Prize, when he got Nobel Prize, then he was giving a lecture. And he recalled an incident happened to him when he was in the high school with his very famous teacher, Mr. Bader. Feynman appreciated him so much. He brings him over and over again. So Mr. Bader found Feynman. Feynman finished all of his coursework before the school starts. So he finished math, physics, everything, and he was just sitting bored in class. So Mr. Bader called him, Feynman, come, I'll show you something interesting. So Feynman now recalling this point, and he's talking about the thing that he showed to him that is interesting, and quoting from Feynman's words in that lecture. He's saying, then he, referring to Mr. Bader, told me about something which I found absolutely fascinating and have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare this lecture, I found myself making more analyses on the thing, and instead of worrying about the lecture, I got involved in a new problem. This thing which he told him about is the principle of least action, which Feynman also used to develop his principles on quantum mechanics and got Nobel Prize for. So what is this? Okay, we can do equations of motion using F equals ma, that's fine, okay. But then, I will show you the history, but if you think about it this way, okay, nature is wise, nature is doing things optimally, so if this object is moving from here to there under the action of F equals ma, that's fine. It may be also optimizing a magic quantity. Going from here to there, a tree leaf is falling, an airplane is flying, a planet is orbiting, all of them, they move according to F equals ma, that's fine. But they may be also optimizing, minimizing a magic quantity. That's okay. So there are many doubts here. But first of all, we have to admit that if this is true, if there is such magic quantity, if it does exist, then the whole science of mechanics now turns into optimization, right? Because if I want to solve for the trajectory, I don't need to go and write F equals ma anymore. All that I'm trying to do now is to find a trajectory that minimizes this magic quantity, right? So if if God told us about his magic quantity, we will be done. And the whole science of mechanics will be turned into optimization, okay? So this is the principle of least action. Let's now see what is the history behind it and what is this magic quantity. So as a recap again, this is our mechanics, classical mechanics. It's Newtonian, vectorial mechanics, in Newtonian mechanics, what's the main equation in Newtonian mechanics? Exactly. So you relate the cause to the effect. First of all, how are you going to quantify your motion? This is a big deal. Because the way you define the quantity of motion dictates how you look at the cause. How are you going to quantify your motion? So we quantify our motion by linear momentum, right? Maybe a vector. Now, our cause, always, we're going to call it a force. And the whole branch of Newtonian mechanics is to relate the cause to the effect. Simply, this is d by dt. The force is the change in linear momentum, right? And this branch has indeed culminated in Newton's Principia. This is what, 1687? Newton's Principia. where he collected the efforts of his predecessors, Galileo, Huygens, and others, and he added his contribution, wrote something very similar to this, no d by dt. On the other hand, so what are the main two quantities here? What are the main two quantities? The main two quantities, linear momentum and the force, and we're trying to relate them. They are both vectors. This is why we call it vectorial mechanics. All dealing with vectors, and you must be tired now from differentiating twice to get the acceleration and dealing with vectors. In analytical mechanics, on the other hand, sometimes we call it variational mechanics. Today we're going to see why we call it variational mechanics. Again, you're free to quantify your motion the way you like. And the same to define your force, the cause of the motion, the way you like. So let's start somewhere in history. I mean, it goes back very far away. Let's start somewhere, some seriousness. I would say the first serious analysis here was by Leibniz, because he said, no, it's not actually MV. This is not a proper way of quantifying my motion. My motion is quantified by actually mv squared. This is a better measure of the motion. It's not mv, it's mv squared. Then your force, you got to define the force now, right? Which is not our force, because this is very prevalent. This is the dominant branch. Newtonian force is our force, right? But whenever you define a new mechanics, you got to define your force. The force, what leads to the effect, how you're gonna change your quantity of motion. So as you guys know, what are the two main quantities in analytical mechanics? Lagrangian mechanics. Lagrangian falls here. What are the two main quantities? Kinetic energy, so that's Leibniz vis viva, right? Twice this guy. Potential energy, which is analogous to the work function. So to Leibniz, in this branch, the cause of the motion, or the force, is the work. And again, okay, you're gonna introduce new mechanics here. What is the relation? What is your governing equation? Well, our governing equation is that the cause is the change of the quantity of motion, right? Okay, and then, so, like I said, Leibniz introduced this quantity, call it vis viva, which is the living force, in 86, actually 1 year before Principia. And then there was a division, a polemic, fight in the community. What is a good measure of the motion? Is it Leibniz vis viva or Newton quantity of motion? So when we say quantity of motion, it's the momentum. Okay? What is a good measure of the motion? mv squared or mv? At this time, if you just look at this, well, there is a major difference. There is a fundamental difference. What's the fundamental difference? This is vector, this is scalar, right? So the two main quantities here are scalar quantities. The two main quantities here are vectors, but actually the community at that time did not realize. So if you look here from day one, you immediately realize that this is not complete. It's not sufficient. Why? A particle in 3D has 3 degrees of freedom. I need 3 equations of motion. This is always one equation of motion, right? But this is vectorial. In the Principia, Newtons did not write the vectorial form of it. And actually it took the community a while to realize that, oh, we need to apply it actually in the vector form. Okay? I mean, if this conception was at the time, there would not be this whole polemic. It actually lasted from here until 1724, where the Academy of Science has to put an end to it, so they made a competition. Okay, the community go and compete and tell us which is the correct way of doing dynamics. So you can see it's like 30 years division, polemic for the community. Because of Leibniz vis viva. Why is this polemic? Okay, I'll tell you. We know since the time of Galileo that I have a particle here during this motion, slides, it acquires force that is sufficient to get it back again to the same elevation, right? So during this excursion, the particle acquires some cause of motion to the ensuing motion. Okay? So during this excursion, the particle acquires some force. Okay, what is this force? Well, the heavier the particle, the larger the force is acquired. So it goes linearly by mass. The larger this elevation, the larger the force it gets acquired. So it's simply mh. You can put g, so it's mgh, that's fine. And mgh is indeed the work done during this excursion, work done by the weight, right? By gravity. So if you agree that your force, the left-hand side, the cause of the motion, goes by linearly by m and linearly by h, it cannot be identified by mv. Why cannot be identified by mv? Because if this is true, the following is true. If I have a mass that is 4m from an elevation h, this should be equivalent to a mass m from elevation 4h. The two situations will acquire the same amount of force. Okay? But then when they come, in these two situations, when they come down here, we know that the velocity nowadays it actually goes by square root 2gh. So it's proportional to square root h. So when they go down the hill, this leads to momentum acquiring mv by how much? The mass times velocity, which is square root h. This is not equivalent to what is acquired here, which is the mass times the velocity, which is square root 4h. You see what I'm saying? So this was the argument by Leibniz followers. It can't be mv. Another thing, I mean this is too tight to write, but I don't know, should I erase this? In actually collision, so let's see. We have here elastic collision. So this is M1 V1, M2 V2. They're gonna rebalance. Okay? So the two velocities coming after the collision are unknowns, and we need to solve them for them. We need two equations. When you look at this situation, I mean, if everything is perfect, you lose nothing. So whatever you quantify your motion by mv or mv squared, it should be conserved. So the summation of mv should be conserved before impact and after impact. Summation mv squared, if this is the right quantity of motion, should be conserved. How do you solve this problem now? I mean, ignore the history. How do you solve this problem now? I have two unknowns, right? How do you solve? I need two equations. Both are conserved. Summation mv squared is conserved, right? So this was a strong point to the Leibniz followers. But we know that summation mv is conserved. Do you think so? If I write summation mv like this, is this conserved? Without vector? No. So this was actually a point against these folks that mv without vector is not conserved. But then they realized in the middle of the polemic 30 years that, oh, we should apply it with vector. So when they add this, now it became constant. So both measures are actually valid in this case. But what about the other case? That I have a big body here, M1, V1, smaller body, M2, V2 in the same direction, and after collision, it's inelastic collision. So they're going to be just one body, M1 plus M2 by V final. It's only one unknown. What do we know about this problem now? Kinetic energy is not conserved. There's some loss and momentum is conserved. So again, this was a point against these folks. Anyway, it was, you can read it in the history, it's polemic on Leibniz vis Vega. It lasted for 30 years, dividing the community, the geometers, defenders about the Cartesian point of view, where Maclaurin, Stirling, over here Leibniz and all of his followers, in addition to Jean Bernoulli and others. I mean, it was really something in the community. I'm just giving you this background. It's not very related to the principle of least action, but this background is important to know what was going on. Any questions so far? Just a historical argument. Okay, going back to the principle of least action. Let's have some history here, so like a timeline. Again, we have to start somewhere. For me, the most serious thing was 1662, and this is Fermat's principle of shortest time. This is for light rays. So we have here something like that, and we have light, theta 1, theta 2, velocity in the light of the light here in this medium V1. This is a different medium, V2, dense, more dense. So the Snell's law, if you remember, sine theta 1 divided by sine theta 2 is just V1 over V2. Okay, Descartes arrived at this law with an incorrect assumption. He assumed that the light speed is higher if you have a more dense material, which doesn't make sense. And Descartes, if you read his stuff, he's very stubborn. He can destroy even physical facts if he believes something. This is why the community is, they go after him so harsh. Anyway, so Descartes arrives here and he has so many followers. They arrive here, it's a correct law but with an incorrect assumption, statement or premise at the beginning. Fermat said, okay, wait a minute, he was a mathematician. What is nature minimizing going from here to there, some point down, in going this excursion? And he found that if nature is minimizing time, it exactly leads to the same law. Okay? So this was, you can say here now we're talking about nature minimizing. Okay. Just for the record, 1686, here we said that Leibniz paper that introduced the vis viva, the living force, kinetic energy, that divided the community for like